Hello again. Today we will be reading the source code for YOLO model, one of the most popular algorithms for object detection at the moment. So in my previous video, I went through the algorithm in detail, and today we will spend some time to actually read the source code, to train such model ourselves, to go much deeper into the architecture, into the actual image transformations, and everything else that is going on in there. So first, a reminder, I am making a series of videos to learn computer vision. So the goal of that was to start with something really simple like digit classification here, where you'd be able to just sit down and solve a simple task in like 50 lines of code in half an hour, just having basic machine learning knowledge and Python programming. And then to keep building up concepts on top of that to bring up to speed in all the amazing stuff that was happening in computer vision recently. So perception, stable diffusion, image generation, all that fancy stuff. So we are somewhere in the middle of that process right now. So in the past, we have started with digit classification, then talked about convolutions, activation functions, optimizers, patch norm, residuals. Then we had a session similar to what we'll have right now, where we actually trained our own ResNet model to classify ImageNet images. So it's a huge data set. It was a famous challenge running for 5 years back in 2015. Then we talked a little bit about object detection as a task. So my previous video was about YOLO algorithm. So I do recommend you check it out as well. And now we are going to train the actual YOLO model and read the source code. So this is the plan for today. First, we are going to actually train the model to reproduce the benchmark basically on a COCO dataset that is the most famous for object detection at the moment. This part is actually much easier than what we had in ImageNet because the dataset is smaller. So the dataset is 20 gigabytes. It will only take a few days to train the model on a proper GPU. And also the YOLOv5 model that we're going to be training, it is created by a company called Ultralytics. And they sort of made a lot of effort to make sure everything is well documented. Everything can be just downloaded from the internet and ran. So it's really quite straightforward. And then I'll show you around the code itself. So I will show some tips and tricks on how you can read the code yourself, like what tools can you use to be able to understand what's going on in there. Then we'll go through basically the data set, so loading and transforming the data. And this is quite important, so you need to understand what data augmentation techniques are used if you want to build a model for your own task, for example. Then we'll go through the model itself and the model architecture. Then the loss. This is probably the most challenging part of it all. So the loss, the handling of the anchors and the grid and all of that. And finally, we'll take a look at the actual training loop. So learning rate scheduling, which optimizers are used, how it all looks like, and so on. Okay, so first, how to train your own YOLO. So here we are going to reproduce the benchmark, which means that we don't take any pre-trained models. We just take the initial data, which is COCO dataset, and just train our own version to make sure it works, to make sure we know how to run it, and it might be useful as well. So to do that, I just go to Google. I Google PyTorch YOLO. So the first link leads me to PyTorch Hub. So this is the place where I can basically get a pre-trained model or get a model that is not trained but is defined somewhere else. And the view on GitHub link points me to a repository. So I'm going to clone this repository now. So this repository is basically the open source implementation of YOLOv5. And back in the description, it also has a link to docs, so YOLOv5 docs that are quite useful. So I learned a lot from reading this. They have different links on how to fine-tune your own model without writing any code, on how to train a model, how to use existing model for inference to just detect something in a picture. So it's all quite well explained. So we're going to go to the quick start page here. So here it says what we need to do to install it. So yeah, we are cloning the repository. Let's go there. Then we need to install all the requirements. So don't forget to do that. And then I'm going to scroll down to this training part. So here they actually have a saved command line command to just train your own model. So I just copy this, wait until everything gets installed, and now I just run it with my proper Python. So it is that easy. So it is now going to run the script. It will download all the data from the internet. It's just 20 GB, so it's fine. It will pre-process the data a little bit, check that it's correct, and then just run the whole training. So it might actually work on just my laptop, but obviously you might want to run it on a PC with like a good GPU. So let's see what is going on in the script itself. So first, let's go over the training arguments. So I launch the train.py script. Then I pass in the sort of configuration for the data called COCO.yaml. So I can go here and open the file that is in the folder data. So data/coco.yaml, and just see what's going on there. So it's basically a short config that describes what the data should look like, the class labels, where to get it from. So we can see that the actual images are downloaded from the official website, and then some of the labels are downloaded from ultralytics. So the COCO dataset, it is open source, so you can just Google COCO dataset. And go to the website, and then there is a dataset/download link that allows you to download all the images, all the labels. It's just about 20 gigabytes, so it's not that much of space. So you can, it's probably going to be useful if you are a computer vision engineer, because at some point you might need to pre-train your models on something like that. So it's good to know where to get that stuff from. And as we can see in the config here, some of the stuff is downloaded directly from ultralytics. So this YOLO script is going to download labels from ultralytics, so the actual bounding boxes for the objects. They're actually available on the official website as well, but just in slightly different format. And ultralytics provide the open source implementation of the script to convert one to the other as well. But it's just easier to work with ultralytic labels directly. They are exactly the same as the official labels from COCO, they're just in a different format. Right, so moving on, then we have passed the configuration for the data, then the number of epochs, which is like the training length that we spent. Then we pass nothing as weights, meaning that we are not fine-tuning any pre-trained model. We're starting from scratch. Then this YOLOv5n, that's basically a configuration file for one of the variants of the model. So if I go back to the docs site, they have several variants of this. So N, S, M, L, X. They just basically different size. So 5X is like 8 times larger, and it will take like 8 times longer to train. So it's a good idea to reproduce starting with 5N, just because it's quicker, but maybe the 5X is going to be the better model. And let's look at the config as well. So I can look at it. It's located in models/YOLOv5n.yaml. So again, this is a short file, and it contains some information about architecture of the model. So which layers are used, how are they connected, and so on. and that's in YAML format. So some Python code is going to parse that and try to convert it to the actual PyTorch code. And don't worry, we will go over that soon enough as well. So now the script has started. It sort of prints out what is going on. So this 1db, it's a tool that is not really necessary to train the model. It's basically a website that allows you to save your launches. So intermediate progress that you can print with TensorBoard. It's also exported to this website. So, you have it available cross device and so on, but we won't really look into that. Then we have some training parameters, like image size, different configurations for hyperparameters of the model. We haven't really specified any of that. So all of these is just default values that the script runs with. And that is what should be used to reproduce the benchmark. But again, if you want to experiment, you might be able to change them later and run an alternative model. Then it says how you can view what's going on in TensorBoard. Then it prints out all the model layers again. So, like, what are they called? The shapes, the different arguments. What is the optimizer? So we're going to use stochastic gradient descent. It is going to have some complicated sort of learning rate scheduling. We'll talk about that later. Then we have this auto anchor script. So basically, if you have watched my previous video, to train YOLO, we need anchors, which are like priors for possible scale and aspect ratio of the object that we can see in the image. And so if none of the anchors match this object, it will not be recognized. So to basically do preliminary data analysis, the script runs the check to just make sure that existing anchors that were defined in our config script, that they are a good fit, meaning that they match most of the objects. So in here it matched 99.5% of all the objects. So that's good enough. So we move forward. And then, the training just started. So we can see that, iterations go. It will take roughly 4 hours per epoch, which is a lot. But yeah, this is laptop, so it should take like 1 day in total on a proper GPU. And that's it. So yeah, it runs. Now we just need to wait. Really, all it took was cloning the repo, launching the script that we had provided on the website. So it's really easy. So now let's discuss, I'm going to interrupt it. Let's discuss what could go wrong. So first we started with installing the requirements, and in here it says pip install -r requirements.txt. So if we print out everything we have in this file, it's just a list of all the libraries that we need. And if you have noticed, I installed it like that. So I'm typing Python 3.9 -m pip install -r requirements.txt. So I do that because there is a problem with different Python versions on your machine. So on my laptop, I have like 10 different versions of them. And you can never be sure if you just type pip, to which Python it's actually connected. So if you type it like this, Python 3.9 -m, it's like calling pip module for this specific Python. So it will always be proper Python. Then let's see what else can go wrong. So the GPU memory. So it's mostly dependent on the size of the model and the batch size. So this is why they recommend to use smaller batch size for bigger model. So if you have limited GPU memory, you might want to reduce the batch size, and then it will sort of consume less memory. And finally, CPU memory. So by default, if you have noticed when running that, it will consume something like 20 gigabytes of RAM, so CPU memory. And this is because it is caching the entire data set in memory, which is quite good because the data set is small enough and usually it makes sense to do that. But then if you don't have extra 20 gigabytes of memory, you might want to disable that. So you can disable that by adding the option of cache and then just empty string. So this will cause the data loader to read from disk every time. So it will make it slower, but then you would not consume this 20 gigabytes of memory. Now let's move on to reading the actual code. And first, let's discuss the tools we can use to sort of help us in that. And that's going to be PDB and Jupyter. So first, I navigate back to the root of this YOLOv5 repository, and I just open the entire folder in Visual Studio Code. So I do that to sort of have code navigation, to be able to jump between definitions and so on. So this is how it looks like. So it's like, 700 lines of code, so quite a lot. But then most of that is condensed in this train function that is basically does most of the work. And that is still 200 lines of code. Right, so first, what's PDB? So this is a Python library that can open the script as GDB, if you know what that is, which is basically an insight into like what is happening inside the script. So now when we started the script in the command line, it just sort of runs and it would run for a day and then it will finish and that's it. So it's no interactivity whatsoever. PDB allows us to break at a specific line, play with it interactively, see what values of the variables we have, and so on. So to use that, I just import it first. I type import PDB. And then somewhere where I'm sure that the execution will reach, I'm just going to call the PDB setTrace function. And what that will do is when I run the script next time, it will stop at this point and it will open the interactive session. So let's see how that works. I'm going to run this and just let it run. It will take some time because script is taking some time to load. Then I'm opening another terminal. And I also want Jupyter Notebook. So to do that, I'm just going to create a file called sandbox.ipynb. So this is Jupyter Notebook file extension. And I'm also going to open it right here in Visual Studio Code. So that sort of helps me keep my code navigation while I am sort of playing with it interactively. So the reason why I want this is that this is like my sandbox where I can type in some functions myself, maybe visualize it more, so display the actual images and so on. And thanks to the fact that we have put this Jupyter Notebook file right at the root of the repository, I can now just copy all the imports, all the stuff that is happening here, and they will still work. So, for example, some of the, I need to configure the kernel first. So I'm running that right here in VS Code. And as we can see, some of the stuff here is just, external libraries like Torch, which is PyTorch. But then some of this is just the files, folders defined right here in this repository, right? So in order for them to work, you need to make sure that the Jupyter Notebook that you use is located right here. So I've copied all the imports, I execute it. It also checks for all the libraries. So while it does that, let's see what happened to our PDB. So PDB stopped where I told it to. So I can type in list to see where I am right now. At this point, I can, if I want to, print out some of the variables. So for example, the variable hype for hyperparameters. I can print it by typing in p space hype. So the syntax is slightly different to Python. This is GDB syntax, but it only has like a bunch of commands that you want. So p prints whatever it is that lives inside the variable. Right, and now the hyperparameter just basically points to the YAML config where it needs everything to load from. Now, the next thing we'll be doing is trying to create a data loader and actually looking at images. So let me see where that is happening. So this is file train.py and the line number 210. So I'm going to add a breakpoint there. So to do that, I type in b space train.py line 210. Yep, and so it has added the breakpoint. Now I just type in one letter C and enter, which will continue the execution all the way up to this point. Right, so it again will take some time. So, oh yeah, it was quite quick. So yeah, now the reason I'm doing that is in order to sort of play around with this data loader, I need all of these parameters, right? And it might not be obvious from the 100 of lines of code before, like what are the transformations here? But thanks to the thanks to PDB, we now can just sort of print all of that out. So I can print train path. Yep, there it is. Image size. There it is. I can print type of that as well if I need. So everything now is ready for me to just, print it out one by one, and then just copy that to my Jupyter notebook. So I'm going to just define it right here. I'm going to create a new cell. I'm going to say train path is this. All right, so this is my basic setup. So I'm using PDB to be able to stop at a certain point, like, something creating the data loader or calculating the loss, print out the values of variables to understand better what is going on inside there, maybe to copy that to Jupyter Notebook to be able to execute that myself and sort of play with it more interactively. Okay, now that I have shown you what tools I use to read the code, I'll show you how I use these tools, and we will look through the code for loading and transforming the data. And then we'll discuss the sort of transformation techniques, the data augmentation techniques used in actual YOLO model training. So to save a bit of time, I'm going to show a slightly different Jupyter notebook. So I will provide the link to this one in the description, but basically there's nothing new here. All that you see here is basically copied from this train.py script, or I looked it up right in PDB to be able to run different functions. So we start with just saving all the labels to just know what is there. So COCO dataset has 80 classes. So the most popular is person, then have bicycle, car, airplane, and so on. Then I do all the imports, and also I wrote my own show image function that takes in the tensor and the labels for that, and it actually draws the bounding boxes and then displays all of that in Jupyter Notebook. And these are basically hyperparameters that, again, I just copied from PDB, printed them out interactively as the script was running. And I also take care of devices. So I just sort of rewrite device to be CPU, because my laptop is becoming quite slow if I am recording and training a model at the same time. Right, so then we run this create data loader. So this is the only function we need to actually get the look at the data. We can see here that it sort of printed out stuff similar to what we have seen before in when we just launched the script from command line. And by now I can actually print out, like display the actual image, right? So again, this create data loader function, it returns the loader itself and the data set. So the data set is like the storage for the data, although it's not necessarily has to cache it, but it knows where all the files are and how to basically retrieve one element per index. So we can say dataset 0, that will return the first element of the dataset. And we can also print out the length of that as well. And the train loader is an iterable. So you can iterate through that using for loop. And it takes care of sort of preloading some of the examples to make sure that you don't wait for disk IO, for example, and transforms in order to get the next batch, right? And we can use our function showImage to actually display what happens there. And so this is an example of what our model will be training on. So I will explain all the transforms that are happening here in more detail a bit later. But for now, you can see that probably the most important one is this mosaic, where we take our image and then append 3 random images to that. And as we can see, most of the image got cropped out, but I still sort of need to recognize that. So I had broccoli, and then this one is called the bowl for food. And most of that is got cropped out, but we still ask our model to be able to detect that, at least during training. Right, and so we can also sort of see that the element of the data set has 4 sub-elements. So the first one is just the image, the batch, in this case it's not a batch, it's just the image. And then the second one is the labels. Third one is the path. So path is just the actual file that you can look at with the original image. And I don't know what the fourth one is. It's usually none. Right, and this is how we can sort of get an element from the loader. So I can just iterate on it using for loop, just break after the first iteration, and then I get these variables saved in my Jupyter notebook. So I have X, Y, and paths as well. Right, so the shape of X is going to be batch size. I reduced that to 4 to fit into my laptop, times the number of input channels, which is 3 for RGB images, basically. And the image size is always going to be 640 by 640. So basically all our transforms, although original images might have different sizes, all our transforms sort of make sure that they are this perfect square of always the same size. And the labels here are a bit more interesting. So you have 6 numbers per object, and then all the objects from the batch sort of got into this Y label. So now, instead of having the first dimension as the batch dimension, the 4 here, I now have 59. And this is going to be different each time, depending on how many objects actually got in the batch. And here we can see like how the actual labels look like. So the first dimension 59 stands for the number of objects. And then these 6 columns, we can try to guess what there are, to be honest. So let me just print out all of them. So the first element here, the first column, you can judge by the number of zeros that it was supposed to be an integer. And it denotes the index of the image that this object belongs to. So the first, 20 belong to the first image, and then we can see some here in the end that belong to the fourth image. The second one is the class. So 39, let's see, 39 stands for bottle, and we can check that, we do see some bottles here in the image. And then we have the 4 coordinates for the bounding box. And this is how the actual image looks like. So it's just integers corresponding to the actual pixel values. And this is, again, the example of an image from the dataset. So this is what our model will be training on. So now let's read the code for the data loader. So you can see the same code in train.py here. So this is the thing that loads all the data. And basically, main part of it is this data set that just initializes the load images and labels object. And then the rest of it basically takes care of multiprocessing, transformation, buffering to make sure that we have some images ready when GPU is ready to process the new image and so on. So let's take a look at this dataset class, load images and labels. So the PyTorch dataset class has interface with two main functions. So init function is for creating the dataset. So at this stage, we do all our sort of indexing. So we look at all the data, we might load it and check if everything is correct, if labels are correct, like bounding box is not larger than the image, for example, or we don't have duplicates, and store them in cache. So the initialization method basically takes care of these technical details like this. So here it sort of opens the file, it converts the labels, it saves the cache, and then loads stuff from cache if needed. It checks out that everything is correct. And we have a bunch of code here to do that. I'm not going to delve into that. Then we have a bunch of helper functions used by this init method. And then the main one is the getItem method. So this one is to basically get an index and return an image corresponding to that index. And this is where all the image transformation happens. So basically it stores all the indices, and then it's going to just sort of load image corresponding to that index and apply a bunch of transformations. So the first one we see here is called load mosaic. So if you think about that, it's quite complex. And this is one of the reasons people say that YOLO model is quite complicated, because stuff like this, and in here, it's not using some third-party library. It's not using like PyTorch transforms. Instead, it's all sort of code written down right here. So it might be a bit hard to read. And the reason it is so complex is because we need to make sure that when we have 4 images to combine them into mosaic, we need to make sure that we transform labels in the same way we transform the image itself. So, so that it still corresponds to each other. So this is what is written here, basically. Apart from that, we have another transformation step right here. So we will actually have a bunch of places in the code that do image transformation. So if you now go here, it again just does some transformations right here with the image. So it might center image, it might sort of look at different perspectives, rotation, scale, and so on. And to actually know which of them work and which of them are actually disabled, I have like a cheat sheet of all the hyperparameters. So for example, this shear here, right? So I can see that it's actually 0 in default parameters. So it's not going to be used in the benchmark. So we can just skip that. And the only one used is this translation and scale here, right? So now after this loading, let's come back to where we were. So I'm back to the getItem method. So basically after, and mosaic is always true, by the way. So mosaic probability is 100%. So I've loaded the mosaic, which took one image that is deterministic, corresponding to the index of the dataset, then took 3 random images from the rest of the dataset, applied a bunch of transformations to that. And this is not it, right? So we also have some more augmentations here called albumentations. So this one uses a library called albumentations here. So it's like an alternative to PyTorch transforms. And they define a bunch of transformations here as well. So random resize crop, blur, maiden blur, and so on. I'll show it in more detail later on. And again, a bunch of transformations defined right here in line. So we augment colors. We don't really use this one. It's disabled, but then we do flip left and right. And then we just return this. So this is the skeleton of image transformation code. So I'm not sort of diving in all of that in detail because, I don't know, it's just quite hard because a lot of these transformations are probably present in PyTorch transforms, but instead of using them here, it's sort of ultralytics own code, and it's understandable. It's an old technology, and when it was written, the PyTorch probably wasn't in the state it is right now. So instead, I'll just go through all the transformations actually used in the YOLO, the one that is sort of reported on the COCO benchmarks and so on. So the first one that is like the easiest to notice when you just look at the first image you loaded from the dataset is this mosaic. So again, it takes an image, random 3 more images from the dataset, and just sort of appends them to this mosaic. And as you can see here, for example, this person got almost completely cut off because of this process, but we still want the model to recognize it as a person and to predict the correct bounding box for that. Then we have this translate transformation, and in the benchmark, it's used with the ratio of 0.5. So what it does is it takes the image and then just moves them up to 50% to the right or left and up and down, leaving this sort of gray area here. And so the reason this is needed is to make sure that the model sort of does not remember the exact picture, and that we explicitly sort of put in this translation symmetry into the picture, because we know that, you know, pizza here and pizza there is the same thing. So the person should be able to recognize that, and so should the model. And also, like the reason, the actual convolutions should be good at sort of having this translation symmetry by themselves. But when we actually apply convolutions, we also use a thing called padding. So it will add 0 pixels along the border of the image when it applies convolutions. And because of that, if you look at like this piece of image, for example, the network will be able to understand that this is something close to the edge because of all the 0 pixels here. And to sort of make the task harder for the model, we randomize the process. So we add this gray padding randomly from time to time to make sure that the image cannot just remember, you know, if this object is close to the border of the image or not. And the reason it's gray, by the way, is because of picture normalization. So in normal encoding in RGB, 0 should stand for just black. But because we normalize the data, so the mean is going to be 0. So 0 mean is something like gray color probably. And also because of this shift, some parts of the image are now cut off. So some parts of the pizza are sort of left outside of the image. Also scale, which is just basically making the image larger or smaller. This one is quite small, so up to 10%. And it uses basically deterministic algorithms to compute the actual pixel values, the same as you would have if you would just, you know, enlarge the image on your computer or on your phone. And it is almost unnoticeable to human eye, but actual pixel values change a lot. So again, we need this to make sure that the model does not remember the training data and does not overfit, and that the model explicitly understands these transformations and understands that, you know, if the scale is slightly bigger or smaller, you can still recognize that as the same object. Random resize crop. So this one was also used when we trained ResNet. You have seen the video. So what it does is it sort of chooses a random portion of the image, crops it out, and then also resizes that randomly to achieve a square. So in here, the initial crop that we have chosen is like a rectangle that is higher than it is wide. Then we cut it out, and then we sort of flattened it out a little bit. So it's again sort of augmenting the picture a little bit. Then we have blur that is applied with probability of only 1%. Converting that to gray, again, this should be recognizable for most of the classes. That should be recognizable. So we want our model to be able to do that as well, even if we don't really have many gray pictures in the dataset itself. This one is basically a technique from working with photos. So I can't really remember what it stands for, some sort of histogram color normalization. So it's basically a tool to enhance contrast without changing the meaning of the picture too much. And you can see that it changes the colors quite drastically, but it's still sort of the same picture. Then the YOLO's own sort of color augmentation technique. So it mostly makes it less recognizable and changes the colors slightly. But again, pizza is still pizza. And then just flipping an image left to right. So you can see that the hand was to the left and now it's to the right. Now that we have seen how the data is loaded and transformed, let's look at the model architecture. So first, let me come back to the train.py script to make sure that we understand at least more or less what's going on in there. So we start with the train function. Callbacks just basically take care of logging and stuff like that. What else do we have? So in some cases, we might need to take care of like distributed mode where the same code is executed on different machines. Again, we will not dive in deep into that right now. Then we have this pre-trained condition. So if we start from an existing model, that's one case. Otherwise, we just initialize the model. And we can see that it depends on the config, number of classes, that's just 80, and the anchors. So all of that was provided in the config. So I'm going to just go to my Jupyter notebook again and just execute it. So yeah, I also have this one line of code copied from train.py that checks the dataset and returns the actual labels. So this one prints how the model looks like. We can also go to this YOLOv5n.yaml. This is the definition of the YOLO model that we are initializing. And in here, it basically has like the actual architecture of the model. So layer sizes, parameters, inputs, outputs. So we will go over that now. And here it's basically the same. So it prints out the layer composition of the model. So first, let's quickly read the model initialization code itself. So I'm going back to train.py. I just right click on the model class and go to definition. You can see here that it's just a reference to detection model. And then in this class, during initialization, what it does is it loads this YAML file, and then it calls this parse model method. So this parse model method is going to be basically iterating over options that we have seen in the config, like here. So I'm going back to config again. So here the main architecture is split into backbone and head. So backbone is something really similar to what we had when we trained ResNet. So it's basically a model that takes in the picture and basically applies a bunch of convolutions on top of that to get out some feature representation of that. And then the head is something that takes this dense feature representation and basically performs detection task on top of that. And so in here, we can see that the main function being used is this eval. So eval is the Python method that takes in a string and then interprets that as Python code. So it's really unsafe. You could have written something like remove all files in the system in the config. But it's really agile in terms of how easy it is to configure stuff. So what we're doing here is we just iterate over lines in this config and then basically evaluate it. So we pass in the actual name of the class that defines the layer and some parameters for that. So now to start reading that, let's sort of take a look at our model and apply it to some pictures layer by layer. So actual PyTorch model lives by the address model.model. So we can see it here. So it has 25 layers. And this config script also has 25 lines defining the layers. And then we just, let's just start with getting a single prediction, right? So X here is my batch of images. And to get the predictions, I just call model from X. And I can see here that the predictions is actually a list. It's not even a tensor. And it's a list with these sizes. So 4 times 3 times 80 times 80 times 85. Then the same one, 4 times 3 times 40 times 40 times 85. And another one with 20 times 20. So let's discuss like what it is. So the first number, the 4, was the batch dimension. So I set the batch size to 4 to save up on memory. Then the 85 stands for basically the different outputs of the model per grid cell. So we have 80 class probabilities that we need for COCO dataset, then 4 bounding box coordinates, and then the final confidence parameter. So confidence needs to be 0 if the model is saying that there is no object there. And then if there is an object, the confidence sort of indicates how sure the model is in the precision of the prediction that it's making. So that's 85 in total. Then the model has like 3 different grid scales. So the same picture is being superimposed with the grid of 20 by 20, then 40 by 40, and then 80 by 80. And then for each of the grid scale, for each of the grid cells, we get 3 anchors. And all of that is going to be just output by the model. So yeah, here is the demonstration of how this 85 coordinates work. So we can imagine that this output of the model is basically a giant cube where each cell corresponds to a certain piece of the picture, a certain cell within the picture. And then for that cell, for each of the 3 scales, for each of the 3 anchors, the model outputs these 85 numbers corresponding to class probabilities, bounding box coordinates, and the confidence. And here is the representation of 3 grid scales. So 80 by 80, 40 by 40, and 20 by 20. So they are all drawn in scale. So this is how the actual grid looks like. So the 80 by 80 is the finest one. And we can see that, yeah, even these 2 sheep that are quite close to each other, they have like 20 cells available. So the probability that 2 objects really get into the same cell is quite small. Same goes for this 40 by 40 cell, and it's hard to see what's going on here, but yeah, it's more or less the same for 20 by 20. And these red patches here represent the anchors. So the model uses 3 different sets of anchors for every scale, and anchors control the aspect ratio of the object that this prediction is going to match, and also the scale. So as we can see here, the sort of central rectangle, the dense area here, is the actual anchor. But then the matching condition allows us to match a prediction that is up to 4 times bigger than each side. So 4 times bigger width or 4 times bigger height. So the total sort of matching area is going to be much larger. But you can see here that for 80 by 80 grid, the anchors are quite small. So I think none of them would actually match any of the objects here. So this 80 by 80 grid will just say that there's no objects because all the anchors, all the priors for the scale in this resolution are too small to match anything. Then for 40 by 40, we have slightly bigger anchors. And they match more or less all of the objects, except maybe this man, because he's almost taking up the entire picture. And then for 20 by 20, anchors are really big, so they will match everything else. So this is how the output of the model looks like. Now let's apply layers one by one to sort of check the intermediate inputs. So what I'm doing here is the big X is just the input batch of images. And so X1 is going to be output of the first layer. And I'm bringing out the shape of the output and the layer itself. So we started with 3 color channels and 640 by 640 image. Then we can see here that it boiled down to 320 to 320, but the number of channels increased to 16. And the actual layer is quite simple. So it's just a convolution. It's typical for sort of image recognition model, object detection model. So a convolution, then batch normalization, and then this COCO activation. So this is a demonstration of senior COCO activation. So it stands for sigmoid linear unit. And as we can see, it's almost the same as ReLU that we've seen before. So it's a bit more smooth near 0. Otherwise, it's almost the same function. And also we can see here that the first convolution sort of expands the number of channels from 3 to 16. Then it has quite large receptive field, 6 by 6, and then a stride of 2. So it's going to compress the size of the image by the factor of 2. And also it has this 2 by 2 padding. We will see that with all the convolutions that we use. So this allows, so if we didn't have padding, then applying a convolution of kernel size 6 would shrink the image by like 2 pixels at every side. And because of that, it's getting hard to just keep track of all the shapes because, 2 pixels there, 2 pixels there, and after every convolution, the output will be different. So instead, we just do padding, which makes sure that unless we have stride, the shape of the output will be the same as the shape of input. So it's just easier that way. And so the first layer is just this convolution followed by batch norm, followed by activation. So is the second layer. So now we shrink the image down a little bit more and increase the number of channels to 32. Right. Then the third layer is a bit more interesting. So here it's called C3, and it's also using this bottleneck block. We've seen that when we trained ResNet. And also we can see some of the convolutions have kernel size of 1. So let's talk about that for a moment. So first of all, a reminder of what is like a 3 by 3 convolution, for example. We can see the input as this sort of collection of images. So for example, with 6 output channels, it's like 6 independent images. And the 3 by 3 convolution will apply this filter to every possible position. And to get the output pixel, it will basically combine the signal from this 3 by 3 area here. And if we look at the same picture from above, we'll see that every input channel is also connected to every output channel. So it's a lot of connections, it's a lot of parameters, and and it scales multiplicatively with the number of input and output channels. So for the 3x3 convolution, we would have 3 times 3 times 6 times 16 parameters if we have 6 input channels and 16 output channels. And so what 1x1 convolution does is it reduces this receptive field to 1. So instead of looking at 9 neighboring pixels, we'll just be looking at 1 pixel, but we'll still have this all-to-all connections between channels. So in this respect, 3x3 convolution can be seen as doing two things at once. So it propagates the spatial information, so it connects neighboring pixels within one image together, and it also does like a interconnection between all the channels. And the 1x1 convolution does only one of those things. So it only connects the channels to each other, but then every pixel is connected to only one pixel in the output. And again, this 1v1 convolution can be seen as some sort of replacement of just fully connected layer that in other networks is usually used when we just need some sort of increased complexity of the function approximation. But obviously we cannot use a dense layer here because first of all, it will have too many parameters because of the sort of size of the image that we have. And second of all, it will lose all the spatial information because it will sort of lose the order of the pixels within the image. So instead, you can think of 1x1 convolution as this generic function approximator that you can just plug in to increase the complexity of your network. Another block that we see right now in our model is this bottleneck. So again, it was used in ResNet. And what it does is it basically combines 1x1 convolution, then 3x3 convolution, and then it connects a residual connection from input directly to the output. So this is a way to basically improve the training of the model. And again, this is like the main introduction in ResNet. But apart from that, it's just pretty similar to convolution, right? So this one takes input with 32 by 160 times 160, and the output is of the same shape. So all of these convolutions don't have any stride, don't have any dilation. So the input size and the output size are the same. And finally, the C3 convolution. So there is a paper about that. I will not explain the sort of motivation behind that. I'll just show how it looks like. So we have our input, 32 by 160 by 160. Then we feed it into the upper convolution, and that one sort of projects 32 channels down to only 16 channels. And then we pass it on to bottleneck that doesn't change the number of channels, and that's it. And then the bottom one here, again, 1x1 convolution that projects 32 channels down to 16. And then we have one set of 16 channels here, and then the second set of 16 channels here. We concatenate that and feed that into another convolution. So after concatenation, you have 32 channels again, and then you pass that through another convolution and you get another 32 out. So the total number of channels in the input and the output are the same, but somewhere in the middle we had projected them down, but then concatenated the output from two sources to get back at the same number of channels. So this is what third layer does, and we'll see that we have a bunch of those C3 convolutions in the network. But it's basically really close to just a single convolution or a bottleneck in terms of what it does. So it takes an image, it outputs an image mostly with the same shape, unless you provide some stride. And also we can see here that we use more 1x1 convolutions than we do 3x3 convolutions, for example. Right, so moving on. So the fourth layer, again, is just a convolution followed by batch norm, followed by activation function. and it projected the image down to 80 by 80 pixels, but increased the number of channels. Then we have another T3 layer, then another convolution, and so on. So right now we are basically following a bunch of steps to decrease the size of the image while increasing the number of channels. And so it lasts until layer 10. Now layer 10 uses this module called SPPF. So let's discuss this one. So SPPF stands for Spatial Pyramid Pooling. And again, there is a paper about that. I will provide that in the description. So what it does is it takes an input of a certain shape, then it passes it through a single 1x1 convolution, projecting it down and reducing the number of channels to 128. And then it applies like up to 3 max pooling layers in a sequence. So we take the output of this first convolution, we feed it into a max pooling layer with kernel size of 5, but the stride of 1. So we're not compressing the size. We're just sort of applying this 5x5 max pooling to every possible position, and we get the output of the same shape. Then we repeat the process and get the output of the same shape again, and then we repeat the process again. So basically this increases the receptive field of this max pooling operation. So after first 5x5, it's going to be 5 pixels, then something like 9 pixels, 14 pixels, and so on. So we end up with something that has computed the maximum over pretty much the entire image at this point. But then we concatenate all the intermediate inputs. So the first one that had no max pooling, the second one with just 1 max pooling, third one with 2 max pooling, and so on. So after concatenation, we get 512 channels, and then we use another 1x1 convolution to project that down to 256. So this is like this mega pooling operation that applies pooling with different receptive fields without, but also using all the intermediate outputs, including the one with no pooling whatsoever, and then just apply the convolution on top of that to basically use all of the information available to compute the result. And so the result of that, again, this spatial pyramid pooling layer didn't change the shape of the output. So the output is still the same shape as the input, but it sort of applied this interesting transformation to that. And so this is the end of what is called backbone. So this is like the feature computation part of the model. And let's spend a moment to try to actually find the source code for every layer as well. So in here we can see that we see the references to these modules right in the code. So if I go to T3, for example, it's really quite simple. So it defines 3 convolutions and a module, which is a bottleneck in this case. And then it applies, module to the output of the first convolution, and then it concatenates that with the output of the second convolution and outputs that. So you can see all of that written here. We can also check for spatial pyramid pooling. Again, this is quite easy. So we have 2 convolutions and max pooling. And then when we actually do the forward step, we apply the first convolution, save the intermediate result, apply max pooling, save the intermediate result, apply max pooling again, saving intermediate result, and then apply second convolution on top of like all the intermediate inputs concatenated together, which is what we've seen before. And this is also what we can see in this config here. So this backbone is exactly 10 layers, convolution, convolution, T3, convolution, blah, 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 ending with SPPF. So now let's try to start reading the actual object detection head. So yeah, 11th layer is again just convolution batch norm activation function. And then we have this one called upsample. Interesting. And we'll see what it is. So upsample increases the image size from 20 to 40. Then we have another history layer. And this one, yeah, so 13 layer is the concat layer, and it concatenates this previous layer, that is the output of upsample, to one of the earliest layer that we had, layer 7. And then we apply T3 convolution on top of that. And we repeat the process a few times. So we can see convolution, upsample, concat, T3 on top of that, convolution, concat, C3 on top of that. So let's discuss what it is. So first of all, what is upsampling? So upsampling is like basically trying to enlarge a small low resolution image. And you can see the demonstration of that here. So obviously the actual upsampling in the network will not operate on this initial image. It will be some feature map that doesn't look anything like a real picture. But this is just a good demonstration. So this sort of backbone compressed our big image to a really small one, like 20 by 20. And then if we just try to enlarge that, so upsample layer does not have any parameters. It's not learnable. It's just trying to approximate the pixel values in the same way you would if you would just sort of try to enlarge the image. And we will see that it's not really doing a good job. So the picture is really blurry. It's hard to understand what's going on in there. But then the actual architecture of the network looks like this. So basically, this part is the backbone that we've seen. So it takes the image of 640 by 640, and then through a series of layers, it increases the number of channels and reduces the size of the image at the same time, until we end up with like small 20 by 20 image, but then a huge number of channels. And then we do upsampling here. So we increase the number of pixels. So we turn 20 by 20 back to 40 by 40 in this really crude way without sort of knowing how to do that properly. But then we have this residual connection back to one of the original intermediate outputs that had this 40 by 40 shape. So what it does is, if we come back to the previous slide, so it's like we had this crude upsampling approximation that we got from just zooming in into low resolution picture. We have something that is close to original in high resolution with more detail present in the picture. And then we feed both of them to some convolutional layer that sees this upsampled version, but the one that passed through much more layers, that had more transformations from the network itself. So it has more information in it now. And we connect that to the earlier but more resolution image to be able to fix the errors in the actual approximation of how pixels should look like. And this is what happens here. So, and because of that, such models are typically called U-shape. So it's really important for tasks like object segmentation, where after condensing an image to like really small one, like 20 by 20, and we need that, by the way, because we want to apply a lot of transformations. We want to have a really complex network with a lot of parameters. And that is easier done on like smaller image size when everything is condensed together. And so when you need object segmentation, that is when you actually need to say which pixel belongs to which image, you would then upsample that up all the way to original size, right? And you'd have all these intermediate residual connections to make sure that you don't lose quality because of that. But in our case, we don't really need this 640 by 640 output, we only need 80 by 80. So we upsample in 2 steps back to 80 by 80 grid. And then, from there we go a couple of steps down again to get this 40 by 40 grid and 20 by 20 grid. So all of that is basically the same convolution output with some upsampling. And that is probably the most interesting part of this architecture. So now, after we are done with the model architecture, it's time to discuss loss. This is actually one of the most curious things in deep learning. So we had some specific bits in the architecture. So we had this T3 block, the bottleneck, residual connections, special pyramid pooling. But other than that, it was just simple set of convolutions. And there is nothing in that that would indicate that, we are doing YOLO. We have this specific grid matching condition where we're looking for an object whose center is in this grid. There is nothing about these 85 coordinates where the first 4 of them should stand for bounding box coordinates, and then 80 for specific classes, and then 1 for confidence. So the convolutions that defines the output in code, they look something like this. So they have 85 output channels, and that's it. So they are initialized randomly. There is nothing in there that says that this one is going to be the height of the bounding box, this one is going to be the probability of being a rabbit, and so on. So all of that starts to make sense only once you define loss. Once you start propagating the signal from the loss back to the network, these coordinates start to sort of take their own meaning. So the first one will become the height, the second one will become the width, the 85 one will be confidence, and so on. So we have to look at the loss to actually understand what the model will predict. So just a reminder, in YOLO we'll have 3 terms in loss. So the first one, the IAU, is basically about the quality of predicted bounding box. And then cross entropy for quality of class prediction. So is it a ship or is it not a ship? And then objectness is a bit more complicated. So it has 2 main components. It's going to be 0 for every grid cell that should not contain an object. So this means the background cells here that really don't have anything. But this also means some cells over here, for example, that might have parts of the object, but not its center. All of these should output that there is no object. And then if there is an object, so for the cell somewhere here, for example, the confidence should also predict the measure of the IU between predicted bounding box and the ground truth bounding box to sort of let us understand which bounding box the model is sure in and which are not. So this is what we'll be able to see in code. And to actually look at that, let's go to our PDB, just launch it from scratch. So I'm launching the train.py again, following just the example command from the docs side. The only thing I did differently is the batch size of 4, just to simplify it. And I'm also going to refer to the code to understand where should I stop. So I'm going to go to train.py. Then I just search for loss. Right, here it is. Then I go to definition, and this is the loss. So this is how it looks like. And the call method is the one actually responsible for computing the loss, knowing the predictions of the model and the targets. So let's just break here. So to do that, I have to remember the full path to the file. So utils/loss.py and the line number 121. So I'm waiting for the script to start up so that I get into PDB and can set another breakpoint. So I'm breaking on utils/loss.py, line number 121. And then just put continue until I sort of appear in that breakpoint. And here we are. So it took some time to start up. It basically repeated the whole process of reading the cache, checking the anchors, and so on. And now we are actually starting the first iteration. And the first time we need to calculate the loss, we're going to sort of stop at this breakpoint. So I can quickly type in list to see where I am. So this is the very beginning of the loss calculation. And then let's just print the shapes of what I get here. So I get P, which stands for predictions, and then targets. These are targets. So P is actually a list, and it corresponds to the three scales that we had. So 80 by 80, 40 by 40, 20 by 20 grid. And the shape of the first one is 4 by 3 by 80 by 80 by 85. So 4 is batch size, 3 is the number of anchors, 80 by 80 grid, and then 85 for bounding box predictions, classes, and confidence. And then the targets is just a tensor. And the first dimension is the total number of objects that we located in the batch in the first 4 images. And then 6 stands for image index, class, and 4 bounding box coordinates. And also I have the cheat sheet right here, and this is the actual image we're trying to detect objects on. So this is the image number 0. I can actually print out everything here. So we can see here the first column is 0, so it stands for the first image. And you can see the objects here. So 53 is a pizza, this one, the big one. Then 0 is a person, 6 is a train. We had a bunch of them here. So this one, and then a smaller one somewhere here. So we can actually sort of see, look at the picture and see these objects, and then look at the tensors and just see how they are represented. So I'm going to switch back to the code. And in here, the very first function that is being called is this build targets. It's a really important one, really dense one. So let's read this one. It basically transforms the targets. So this tensor of number of objects by 6 dimensions. It transforms that into our sort of grid, into the 80 by 80 or 40 by 40 cells. It takes care of anchors and so on. So it starts on line 178. So you can quickly put the breakpoint there and then type C to go there. Right. So let's read this line by line. So in here, we're just defining some variables that we are going to use. So AI are anchor indexes. Gain is like a multiplier that we'll use to transform the initial labels that are from 0 to 1, and they correspond to like bounding box size divided by the scale of the picture. And we will transform that into our 80 by 80 grid. So every coordinate will be from 0 to 80 instead. And in here, we iterate from 0 to our number of layers. So 3 iterations in total. So first we'll look at the most fine grid, so 80 by 80 grid, and then take care of all the objects in there, and then do the same for 40 by 40 grid and 20 by 20. So let's just continue until here and see what happens. Right, so yeah, this final one is the actual multiplying. So now I can print out the T here, and we can see what transformations it got. So now it has an extra, let's just print shape as well. So now it has an extra coordinate that stands for anchor. So this first big block here is for the first anchor, then this one for the second anchor, and so on. And everything else is the same. So you can still see the pizza, the train, and these are the actual bounding box coordinates. And now they are from 0 to 80. Now, and t is just the number of targets. So we see if we do have any targets, and we calculate this ratio. So let's see what this is. So the targets from 4 to 6, these coordinates represent the height and width of the bounding boxes in targets, in the ground truth. And then anchors, these are just the anchors. So the actual values for the height and width of the anchor in the current scale. And we can see that they are quite small. So the biggest one is only 4 pixels wide. But then this condition allows, let's see what the anchor t, what's the value for that. So this anchor t constant is 4. So having an anchor with up to width of 4, I'm going to multiply that by 4 again. So it's up to 16 out of 80 pixels. So it will not match everything on this picture, but it will match a lot of stuff. So let's print out R. Right. So R is now of the same shape as we had the number of objects and the number of anchors. And then the numbers here basically correspond to the ratio. So the ratio of the width of the ground truth object divided by anchor, and the height of the ground truth object divided by anchor. And then we compute this j tensor here, which is basically comparing this ratio to our max threshold, which is 4. And so some of them will get filtered out. So let's see how that happens. Right. So the shape is now 3 by 43, right? Let's quickly compare that to, so it's just a Boolean tensor, right? And then we filter everything with the condition of true, right? So now t reduced a little bit. We had 43 objects, and now only 35 of them are left. Now if we print all of that out, we'll also see that some of the objects actually matched more than one anchor, right? So let's see. Right here, for example. So we had this person with coordinates 74 and 64, and this person matched the first anchor as well as the second anchor. So it's really interesting, right? So we've talked about non-maximum suppression before, where the network itself will output some duplicates, and then we have to filter them out using a condition. So this is like one of the places where it just happens, right? So we now require our network to predict the same object twice because it matched 2 anchors at once. So we had 43 objects. Some of them didn't match any anchors. Some of them matched 2 anchors. So we got something really unpredictable, 35 coordinates now. Then this piece of code, I honestly going to say that I don't understand everything that happens in there, but I know what it does because I can just print out the results. And basically what it does is it tries to now match these actual specific numbers. So 49, 79, 74, 84, and so on, to specific grid cells. So now we sort of see where this object with 49 x coordinate and 79 y coordinate, which cell will it belong to? So yeah, let's just scroll until the end and just see what we see. So it's quite a lot of code here. Right, and here we are. So now we have this 4 main results for indices, boxes, anchors, and classes. So indices 0 stands for indices for the first layer, and they contain image, anchor, grid X coordinate, and grid Y coordinate. So what I'm going to do now is just a little demonstration of what we got as a result. DCLS from 0. That's going to give me just the tensor of all the classes of all the objects that match some grid cells. So I can print out the anchor for all such indices that had a train in it. So train was number 6. Let's just compare it like that. So you can see that the anchors are the anchor number 1 and number 2, starting from 0. All of the trains were on the first picture. And then this is the X coordinate and this is the Y coordinate. And this is really interesting, right? So we had just, one train, I think, that matched some anchors over here, right? So you had more than one in the initial picture, but then after checking this condition, only one of them remained. So this one, and then this one matched the second anchor. And this is the same one, as you can see from the actual coordinates. And now we have 1, 2, 3, 4, 5, 6 of them. That's interesting. So each of them matched, so one train matched 2 anchors. So now each anchor matched 3 grid cells. And we sort of can see why. So this, the initial coordinates were 62.48 and 78.89. So it's a non-integer numbers. And then they matched the grid cell 62 as well as 61. And then for the X coordinate 78 as well as 79. And you keep doing that for different objects and just to keep looking at the actual image. So I did that. And basically what I found out happened was that some of the objects, after matching to some anchors, will also match several grid cells at once. So we actually want our model to say that the 2 neighboring cells, so for this train, this will be like this one in the middle here, and then this one near that one. We want both of them to predict that there's a train. And this is just how the code is written. This is how the implementation is done. I don't think it's necessary to do it like that. Maybe it's just a mistake, I don't know. Either way, so this is what this function of build targets does. So it takes the initial objects, which is raw coordinates for bounding boxes. Then it filters them out, throwing away those that didn't match any anchors. And then it tries to match these sort of non-integer coordinates to specific indices of the grid. So now these coordinates and these coordinates, those are integers, and we'll see how they are used later on. So let's break on the next line after this build target, so it's 127. So now I'm back here. So I've built the targets, saved them to these objects, and then I start iterating over the layer predictions. So each layer here corresponds to just one scale. So 80 by 80 grid, 40 by 40 grid, 20 by 20 grid. Then I select these indices, and then I do what is called target subset of predictions here. So let's get there in PDB and then discuss what is actually happening. So I'm just iterating forward until this line. Right. So let's first bring the shapes of all the objects here. So first for the indices. So they all have the same shape, 103. So basically I started with 43 objects that got into the batch. Then some of them didn't match any anchor on that scale, so they sort of dropped off. Some of them matched more than one anchor. And then after that, some of those matched more than one grid cell. So out of 43 objects, I now got this 103 matches in total, matches to grid cells and anchors. And I receive basically the tensors with classes, labels, and all the coordinates as just the array. So a bunch of arrays of the same size. And then I do this really intricate subset. So I take the PI, which is the prediction for the current layer. So let's put in the shape of that as well. So PI is 4 by 3 by 80 by 80 by 85. So 4 predictions for every image, 3 predictions for every anchor, 80 by 80 for every grid cell, and then 85 numbers in a prediction. So I use the first 4 coordinates here and just index them using these 4 vectors. So in result, I get one vector where basically everything was matched. So I had this huge grid, 3 anchors per grid and 4 images, and then I leave just one cell, one or 2 cells per grid, 1 or 2 anchors, and so on. So now I sort of throw away every grid cell that did not match to anything. And I get back just this tensor of those grid cells that did match something. And then I also sort of split that out into 2, 2, 1, and 80. So I split 85 numbers into X and Y coordinates, width and height, confidence, and the actual class probabilities. So now if I print the shapes of that, there's going to be 103 by 2, 103 by 2, and so on. So this is the moment where, as we discussed before, where we had this just equal numbers with nothing in the architecture itself saying what they should mean. Now we are defining what they mean. So now we're saying that these 2 will be X and Y coordinates, these 2 will be width and height, and so on. And then we just compute the actual loss. So we have these target subset of predictions, which are just numbers of cells which did match to some object, and they have the same shape as the target. And now we just compute the loss. So we compute the IOU. We can see here that we had some transformations. So width and height actually predict the square root of width and height of the anchor of the object. So we had to square that and so on. Also, we can see here that the actual loss uses IOU, which is not differentiable. So they have this C IOU instead, which is complete IOU. It's like a slight modification of IOU that makes it differentiable. So in here, the L in L box stands for target, for loss. So this one will actually be used for computing the gradients. Then the same for classification. And now this objectness block is basically taking the IOU values that we have calculated and then populating the big array with every grid cell with those IOUs so that we can also calculate the objectness score. And here is where we calculate the loss from objectness. So now let's scroll down here in PDB. Right. So now objectness uses this TObj object. So let's print its shape. And then the PI, the 4th element of PI. So now they have equal shape. And as you can see here, the objectness loss uses all the grid cells. So 4 by 3 by 80 by 80 means that we use all the grid cells, including those that didn't match any object, to compute this loss. So again, coming back to our image here, this is basically saying that the first two terms here, the IAU and cross entropy, they are only defined for only a bunch of cells in an image. So only these ones. Although they did match like a couple cells, a couple anchors, it's still the minority of all the cells. And then the objectness score, it will be defined for everything on the picture. So all the background cells, the cells that are supposed to contain object, and then the cells that only have a part of the object but not its center. So objectness score sort of controls the sort of appearing of phantom objects in the background or of the duplicate bounding boxes from the neighboring cells and so on. So this is about it, about the loss. Another interesting point in that, so if you again look at this picture, one of the big problems in object detection as a sort of scientific problem in deep learning was just the complexity of the loss. So compare that to image classification, where the signal for every training example is really simple. You either got it right or not. So you predict just one class per image. Is it a sheep? Is it a dog? Is it a man? And then if you did correct, then it's a positive signal. If you guessed wrong, then it's a negative signal. In here, it's much more complex than that, because we have this complex combination of three losses. And this matters especially during the beginning of the training, when everything is randomly initialized. And so you'd have random predictions in the background. You would have awful predictions of the bounded boxes for real objects and all that stuff. And all that stuff sort of generates a lot of signal for all these three terms. And if you are not careful about how you sort of weigh all of them and how you approach the general problem, you would have just one loss dominating everything else. And then the network will basically converge to some weird state where all the cells predict nothing, for example, or something like that. So one of the few sort of ways to combat that were focal loss and positive freeweighing. So focal loss is the one that lets you say that I'm using cross-entropy loss, but then I'm going to weigh examples that are misclassified more than everything else. And then the positive weighting just lets you give different weights to positives and negatives. So positives are actual real objects, and you can sort of weigh them higher because there is much less of them. So out of 80 by 80 grid, 3 anchors, that's like 20,000 cells and only 7 real objects. So you might want to weight them higher than negatives. But we can see here in the hyperparameters, so the actual focal loss is defined in the code. The positive weight is defined in the code, but the actual hyperparameters for that just basically disable them. So they're not used in YOLO. Finally, when we read the code for loss here, so we only looked at the first iteration of this loop. So here we iterate over all the scales, so 80 by 80, 40 by 40, and 20 by 20. And we've seen that on the 80 by 80 scale, most of these objects actually didn't match any anchors. So this pizza here is too big, so it didn't match any anchors on this finest scale. But once we get to higher layers with lower resolution, but also bigger anchors, they will match everything. So this pizza will make it to the result, to the loss on the second layer and the third layer and so on. So we actually see most of the objects and feed them into the network, just not on all the scales. Now, I also want to quickly go over the training loop, the code itself, and some unusual stuff that is different from previous model that we've seen. So first, I'm going to train.py. So again, by now we have read some parts of this train function, and it's quite easy to read when you know what to expect. So in all the PyTorch training scripts, we would see a model, a data loader, an optimizer, and then the actual training loop that iterates over the data loader. And in here, we can just look for optimizer, for example. And you can see that it's initialized on line number 177 in the function called smart optimizer. So what it does is it defines different parameter groups. So it uses three main ones, the biases, the weights, and then the batch norm weights, which are considered to be different to everything else. And they will have slightly different learning rate schedules, slightly different parameters, so different momentum, for example. And we'll see in a minute how exactly that looks like and why it's used. And finally, the scheduler. So it's in here. It's the so-called lambda scheduler that basically takes an epoch in and then just computes an arbitrary function provided by the user, this one. And down here in the actual training loop, over here, there is an extra condition for the warm-up. So in here, we actually see how many steps we trained for. And then during warm-up, first 3 epochs, we'll also change all the learning rates a little bit and the momentum. And here's how it looks like. So I have different scheduling for biases and weights. And so in the first 3 epochs called warm-up, the learning rate for weights is effectively 0. So we're not actually training the main parameters in the network. And we just spend the couple of epochs mainly training biases. And that is exactly what is needed to sort of tune down that background noise to make sure that most of the cells will not output any objects and so on. And then after every step, after every batch, we'll linearly change the learning rates. So for biases, it will go down. And then for everything else, it will go up until the third epoch. And after that, learning rate schedule will just linearly modify learning rate until it goes down to a small number towards the end of the training. So this is all I wanted to talk about regarding reading the source code of YOLO. So do let me know if this is something you are interested in, if this is helpful, if it's at least understandable what I'm trying to say here. And if you do, then just subscribe, click that like button, maybe leave some comments. So in the next video, I'm going to look at the DETR model, which stands for detection with transformers. So transformers that came out in 2018 were a major revolution in deep learning. So pretty much everything we see today with big language models, ChatGPT, and so on, all of that started with transformers, where models became really quite good. And transformers are sort of like a silver bullet in the field. So every network that has transformers tends to be better than the network without that. So we'll see at the architecture of the main model, the first model that started to use transformers, and we'll see that it's actually quite a bit more simple than YOLO, and it's actually quite good. And current object detection state-of-the-art models are basically modifications of the same DETR model. So stay tuned and see you soon.